Well, now we're going to learn, or begin to learn, how to apply the method of partial fraction decomposition in order to solve complex integrals. And the example that we'll start off with a relatively easy example, and it will be the integral of 2x plus 1 over x squared plus 2x minus 3 dx. Now what we're going to do is we're going to take the integrand here, and we're going to define some function f of x, and we're going to say that f of x is equal to the integrand. So 2x plus 1, and that is over x squared plus 2x minus 3. Now what we will realize is that f of x is actually equal to the ratio of two other functions, and I will write p of x over, and for our second function we will say q of x. Now if we say p of x is equal to our numerator of f of x, so p of x is equal to 2x plus 1, and our q of x is equal to our denominator, so x squared plus 2x minus 3, then what we will realize is that f of x is equal to the ratio of polynomials. These are both polynomials. And a function that is the ratio of two polynomials is a rational function. So we know that our function f of x is rational, and that is very important. The other thing that we can realize is that the highest power term of our numerator is 1. We see the highest term is 2x, and then x is to the power of 1. And the highest power term, or exponent rather, in the denominator is 2. And since the highest power exponent is in the denominator as opposed to the numerator, we know that this is a proper fraction, a proper function. Okay, so those two things are very important for us to be able to apply the technique of partial fractions. If we didn't have a rational function, let's say we had some other function, and I will call that function g of x, and we will use purple. G of x is equal to, oh boy, we can say, let's say we had the tangent of 1 over x, and we had that multiplied by e to the x over sine of 2x. That's a pretty extreme example, but this would not be a rational function because the numerator, neither the numerator nor the denominator are polynomials. And if we had one other example, and I will say if we had h of x is equal to, well, let's say we had 2x squared plus 1, and that was over x plus 3. We would realize that the highest power exponent is in the numerator because we have an x squared on top and an x on the bottom, and this would not be a proper fraction, a proper function. This would be an improper function, and we would need to apply the technique of long division in order to get it into a proper form that we could use. And I will explain that technique in another video. So now we can look back to our integral here, and we realize that we've satisfied the two conditions, that our integrand is both rational and proper, which means that we can apply the technique. So I'll rewrite the integral. We have the integral of 2x plus 1, and that is over x squared plus 2x minus 3 dx. So in order to, well, how are we going to do this technique? So we'll rewrite the function here, and what we're going to do is we're going to find the factors of the denominator. So we know that we can factor this into x plus 3 and x minus 1. And just checking here, if we multiply these together, we'll have an x squared minus x plus 3x, that equals 2x, and then we'll have a 3 times a negative 1, that's a negative 3. So good. The idea is that we can actually set this equal to two fractions that are added to each other, and we will say this is equal to, and I will use another color here, a, and a is over x plus 3, one of our factors, the first factor, and we're going to add that to another fraction, and I will use orange, plus b, and that is divided by our other factor, which is x minus 1. So we're going to split this up into its essential units here, and then what we're going to do is we're going to multiply both sides by the denominator of the left-hand side, and when we do that, we're going to cancel out a lot of terms. So on the left-hand side, we'll get 2x plus 1, and that equals, well, an x plus 3 will cancel out here, and we'll have an x minus 1 there times a. And then on the next term, the x minus 1 will cancel, and we'll have an x plus 3 times b. And we'll write b there. Now, in order to solve for a and b, we could distribute them out, and then there's a way to solve for them that way. The easiest way is just to choose values for our x's. So the first thing we will do is we will say, okay, well, if x equals 1, well then on the left-hand side we'll get 2 times 1 plus 1, which is 3, and that's equal to, well, the 1's going to cancel out here when we have the 1 minus 1 times a. So then we'll just be left with the next term, which is a 4 times b. And this is equal to, well, if we divide by 4 on both sides, we'll get b is equal to 3 over 4. Now, if we choose our x to equal -3, and notice we're choosing the value that's going to cancel out the b, then what we will get, well, on the left-hand side here, we'll get 2 times -3, which is -6 plus 1 is -5, and this is equal to -3 minus 1 times a, which is -4, and we will multiply that by a, and then our b term will cancel out, and we will know that a is in this case, our a is equal to 5 over 4. So what we've done is we've started with this rational function on the left, and we've created 2 rational fractions on the right that equal that original one through the property of addition. So we can plug in our a and our b now, and we get 5 over 4, and this is over x plus 3, and this is plus 3 over 4 over x minus 1. And now if we take the integral of this is the same thing as taking the integral of our original function, which we're trying to solve. And well, let's split this into 2 integrals. So we know this is the integral, and I'm even going to take out the 5 over 4, and we'll get over 1 over x plus 3 dx, and then plus 3 over 4 times the integral of 1 over x minus 1 dx. Well, these integrals are rather easy. We just recall that we need to take the natural logarithm of them, and that is the integral here. So it's the natural logarithm of the absolute value of x plus 3, and then plus 3 over 4 times the natural logarithm, the absolute value of x minus 1, plus our constant of integration. Now you could combine these. I think it's best just to leave them in the form that they are, but that is the answer to the integral. We solved it using the technique of partial fraction decomposition. There are a couple of more examples that I will share in the following videos. The technique is pretty straightforward, but there are some examples that are a little bit more complicated, in which you need to change the technique just a little bit. But that was it. I hope you found the video helpful. If you have any questions, please leave a comment below, and I will see you in the next video.